Okay, I'll run through this example 3 here. I'm going to draw a quick picture first. My artistic skills, but I will do my best. So we've got a road, we've got a car, and this is a rear view of the car. So the car is moving away from us. Maybe we can get a clue of that by putting some taillights on the car. So there's the car, and it's moving straight away from us, but it's curving. Think of it curving maybe around a curve that's to the left, and then it's going to go around behind us and come back around and pass us, and we'll see it going away from us again. So there's a couple things that are important details to understand from the reading. One of them is coordinate system. They talk about a, a new, not an XYZ per se type of a coordinate system, but a radial, tangential, and Z direction. So the straight inward toward the center of the circle, if the center of the circular path is to the left on our paper, then we can call that the radial direction. I'm not really going to do a great job of trying to draw in 3D, but straight forward in the direction of the car, so the direction of the velocity of the car, you can think of as the tangential direction. And then straight upwards, straight up towards the sky, you can think of up as the Z direction. So straight up, not like normal, the normal force direction, but straight up towards the sky from this center point of this coordinate system could be our Z direction. And so on page 207, 206, 207, that's a little farther forward, but I'm going to throw it at you right now because did they show you that in the earlier part of the book? Yes, they did on page 195. So I'm not jumping ahead. But we've got to set up our forces that lead to our centripetal acceleration according to a coordinate system that will give us the direction that's straight towards the center of the circle. So centripetal or radial are the two different notations that the book will sometimes use there. So how do we do this? First, we go to our free body diagram, and if we look at our free body diagram, it should look like the normal force. It should have, of course, force of gravity. And in this case, there's zero friction. So the only thing that leads us to having this inward radial force, so we need to think of a radial force inwards so that we can use the concepts of Newton's second law where the net force produces in this case, radial or centripetal acceleration. And that net force comes from the inward component of the normal force. So this could be thought of as the normal force in that Z direction, and then there's a normal force in the radial direction inwards, and the radial force is the one that is our net force. There's no friction. The inward component of gravity, if we were to still think of our XY axis to be like Y and X like this, X does not point straight inwards. It points down the hill and below toward some point below the center of the circular path. So that is not the centripetal force. So that radial force from the normal force that is created by the slope of the road is then going to be equal to mv squared over r. We put v squared over r in for AR because we need to talk about things in terms of the speed that the car is traveling and the radius of the banked curve. Okay, so now the problem here is we need to figure out what angle that the road needs to be banked at so that just that radial force from the normal force keeps us in a nice constant radius path, meaning we're not sliding down the hill to shorten up the radius of the turn, and we're not sliding away upwards on the hill, like you might have seen in a NASCAR crash or something like that. You can slide uphill. Newton's first law says your car wants to keep going in a straight path. It doesn't care if the road's curving in front of you or not. So that's that inertia idea is why we need just the right speed here, so that friction is not a factor and you don't exceed the amount of radial force that the track itself from the normal force inward can produce. Okay, so that was a long intro. Well then, the problem is we need to introduce theta so we can solve for it, and we don't exactly have a value of the normal force, but we can eliminate it like we usually do. So how do we find or how do we set up this radial force? So if that radial force is the one that's in the straight in toward the center of the circle, or some of the forces in the radial direction, back to the v squared over r, this normal force in the inward direction is going to be n sine theta. Okay, well, talk to me about theta for a second, you might be saying. Theta, the hill angle here is going to be our theta. And in our diagram, if I extend this direction backwards for our normal force, that, like usual, is going to also be theta, and then the vertical angle from that is going to be up there in the normal force triangle. So those are all the same angle that we're looking for here. So n sine theta, that would be this radial one up here, equals the radial force, and so set that equal to mv squared over r. All right, well that gets us theta introduced, but normal force is still kind of unknown. So why don't we do this? Why don't we then go to eliminating that? So we could say that the sum of the forces in the z direction equals 0 because there's no up and down acceleration of the car, and so that would be n cos theta. That's the component of the normal force in the z direction, and then gravity is opposite of that, so that'd be minus mg equals 0. So we could kind of quickly kind of rearrange this to say that the normal force is you could do two things. You could say it is equal to mg over cos theta, but I'm actually going to kind of maybe stick with just n cos theta equals mg. And I'll come back to which one you like better for whatever reason in a minute. So we could solve it for n and then plug in mg over cos theta right here for n. And it's really kind of 6 of one, half dozen of the other, whichever way you want to do it. I think I just changed my mind. Let's take this expression and substitute mg over cos theta in up there for n. So if we make this substitution, then we're going to have mg over cos theta times sine theta equals mv squared over r. First thing that I would do is just kind of clean things up if you can, so we can get rid of the mass. It's on both sides, and then you might notice sine over cosine, we could rewrite that. So we could rewrite that as g tan theta. So g tan theta equals v squared over r, and tan theta then is, I'm going to move this out of the way. Tan theta then is going to be v squared over rg. And if you plug in the values and do an inverse tangent, you should get a theta of 15.5 degrees. You could have went to this step and plugged things in, but I think it makes life a little shorter and easier if we would have done it with plug in the mg over cos theta right there for the n. So quick summary, we need a vertical axis that lines up. It just happens to line up nicely with the force of gravity and gives us a way to eliminate the normal force from our equation as an unknown. We need an inward force, and so that inward force causes the centripetal acceleration to happen, and there's no tangential force like straight into the paper following the car at that moment, straight forward. There's no tangential force, and that's why we have a constant speed. We don't move faster in our car, thereby changing the need for a larger centripetal force to make us turn or anything like that. So a z component is what they want to use in the book for a vertical system, a radial component inwards, and then that tangential one is not going to be a factor now, but it will be later on in this chapter when we do speed up, and then centripetal acceleration changes as we go faster in that v linear sense. So I'll break the video here and then do that last example in a third video.